Okay, let's jump right in. We're unpacking a fantastic new paper today. Future as Label, Scalable Supervision from Real-World Outcomes.
Yeah, this one is a big deal. The authors introduce a concept they call Foresight Learning, and it really tackles a core problem in, making AI useful in the real world.
Right. So the problem they're addressing is that something like reinforcement learning with verifiable rewards, RLVR, great, but it's kind of stuck in a sandbox.
Exactly. It works brilliantly when you have immediate, clean feedback. Think about a math problem or code generation where a unit test either passes or fails. It's black and white.
But the real world is messy. If you ask a model to forecast, say, an election result 6 months from now, your feedback, your reward, is super delayed.
And it's sparse. You only get that one signal at the very end. So what this paper does is it builds a whole framework to use that delayed objective outcome, the future, basically, as the supervision signal itself.
And it does this by being incredibly strict about information. The model can only see things available at prediction time, time t, and it gets its reward way later at time t when the event actually happens.
And here's the headline result, the part that really got everyone's attention. A Qwen 332B model, so a 32 billion parameter model, trained with this Foresight Learning. It didn't just get a bit better.
No, it crushed it. It improved its Breyer score by 27% and literally cut its calibration error in half.
But here's the kicker. That 32B model outperformed a much, much larger Qwen 235B model.
That's the part that's just stunning. It wasn't even close on both synthetic data and the independent Metaculus forecasting benchmark.
It's just this perfect proof that smarter supervision, a method that actually respects how time and information work, can be a way bigger lever than just throwing more parameters at a problem.
Okay, so let's dig into that a little deeper. The motivation. Why exactly does RLVR work so well for something like coding, but just fall apart for forecasting?
Well, like we said, those are closed world problems. A theorem is either proven or it isn't. The environment is deterministic.
But the real world is anything but. You're trying to predict a court case or what the Fed is going to do with interest rates. These things unfold over a long time, and the outcome has nothing to do with what your model said or did.
Right. There's this natural temporal asymmetry. The information you have today to make a prediction is fundamentally different from the information that will exist when the outcome is known.
So you could have a great reasoning process today that leads to a wrong answer or a terrible process that gets lucky, and you won't know for months.
And what the authors realized is that this asymmetry isn't a bug, it's a feature. It's the perfect structure to build a scalable learning system around. They turned the arrow of time into a reward signal generator.
Which feels totally different from, say, standard supervised fine-tuning, SFT. With SFT, you're usually just trying to mimic a human-written answer.
That's a key distinction. SFT is about matching a target. Foresight Learning has no intermediate targets. There are no human annotations on the reasoning process.
So it's not learning to sound like a good forecaster.
No. It's optimizing its entire internal process, its policy for thinking, based only on whether that process leads to a well-calibrated prediction that aligns with the eventual objective truth.
So the goal shifts from get the right answer to have the right level of confidence.
Precisely. It's about optimizing decision quality under uncertainty, which is frankly way more useful.
Okay, this brings us to the how, the methodology. The absolute bedrock of this whole thing seems to be what they call causal filtering. How did they stop the model from, cheating and peaking in the future?
This part is so important. They are incredibly strict. At prediction time t, the model's input context contains only information with a timestamp of dead or earlier.
Even for events that happened years ago in the training data.
Even then, they're replaying history as if it were happening now. Any document, any news article dated after that prediction time is completely masked from the model's view. No leakage.
And to enforce this, they set up two different roles with asymmetric information. The predictor and the resolver. Let's start with the predictor.
The predictor is the model we're actually training, the 32B Qwen model in this case. It gets the event question and all that causally filtered timestamp text. Its job is to think, to sample a reasoning trajectory and then output a single number, a probability P.
A number between 0 and 1, and the resolver.
The resolver is like the objective historian who shows up later. It's a separate frozen large language model. They use Gemini 2.5 Flash.
Frozen meaning it's not learning or changing.
Right. Its only job is to look at all the information available after the event has resolved and determine the ground truth. D. Did it happen? Yes or no, 1 or 0. Crucially, the resolver sees all the future information that the predictor was denied.
But wait a minute. If another LLM is deciding the ground truth, isn't that just replacing one noisy process with another? Could the resolver be wrong?
That's a totally fair question, and the paper acknowledges it. An automated pipeline could introduce noise or bias, but the key is that the resolver's judgment is only used to provide that final binary outcome. It's never used to score the quality of the reasoning or the prediction directly.
I see. So the learning signal is still purely about the gap between the predictor's constrained view and that final external outcome. The separation is what matters.
Exactly. Now, about that learning signal, the reward function, they use the log score. Why that specific formula?
Yeah, without getting into the weeds of the math, what does it do?
It's what's known as a strictly proper scoring rule. And what that means is it mathematically guarantees that the model gets its highest possible expected reward only when it reports its true internal belief.
It incentivizes honesty.
It actively punishes dishonesty. Let's say the model internally thinks there's a 70% chance of something happening. If it predicts 0.7, fine. But if it gets cocky and predicts 0.9, the log score will hammer it if it's wrong.
And if it's wildly overconfident, say 99.9%, and gets it wrong.
The penalty approaches negative infinity. It's a very, very powerful signal for forcing the model to be calibrated, to be honest about its own uncertainty.
So you're not just optimizing for accuracy, you're optimizing for well-calibrated accuracy.
Right. But it's important to remember this is not just supervised training, even though the reward looks a bit like a likelihood objective.
Because you're using policy gradients. You're reinforcing the whole sequence of thought.
Exactly. You're treating the model as an agent making a decision under uncertainty. The reward reinforces the entire reasoning trajectory that led to the probability, not just the final number itself. It's a subtle but really critical distinction.
Okay, so that leads us to the big optimization problem. A single reward, months later, for a stochastic outcome. The variance in that signal must be astronomical. How on earth do you stabilize training?
That is the core technical challenge they had to solve. And their solution is, I think, really elegant. It's an algorithm called Group Relative Policy Optimization, or GRPO.
GRPO. So what's the mechanism there?
Instead of the model generating just one line of reasoning for a given question, it generates a small group of them. In the paper, they used a group of 4.
So 4 different internal monologues, maybe leading to 4 slightly different probabilities.
Yep. Then you wait, the event resolves, and you calculate the log score reward for each of the 4 trajectories.
Okay.
But here's the clever bit. You don't update the policy based on the absolute reward. Instead, for each trajectory, you calculate its group relative advantage.
Meaning you compare it to the average of its peers.
You subtract the mean reward of the group of 4 from that trajectory's individual reward. So you're rewarding reasoning paths that did better than the average attempt from that exact same starting point.
Ah, I see. So even if all 4 trajectories were pretty bad because it was a really hard, unpredictable event.
The ones that were slightly less bad, maybe a bit less overconfident, will get a positive update signal.
It filters out the noise from how hard the problem was. You're isolating which reasoning strategies are genuinely better given the same limited information.
It's a brilliant way to stabilize credit assignment when the feedback is so delayed and sparse, it makes the whole thing tractable.
Okay, let's talk experiments. The data set itself sounds like a major engineering effort.
Oh, for sure. They built a data set of over 5,000 binary questions, politics, economics, you name it. But the key was that causal purity. Every single source document had to have a verifiable timestamp. Anything ambiguous was just tossed out to prevent any possible leakage.
And they were really strict about separating the training and test data in time.
Absolutely critical for a forecasting task. Training was all on predictions made up to January 30th, 2025. The test sets, both their synthetic one and the Metaculus benchmark, were only predictions made on or after February 1st, 2025.
A true out-of-time validation. And the baselines they compared against were pretty tough.
Yeah, it wasn't a straw man. They compared against the base 32B model, an ensemble of that model to control for variance reduction, and of course the big one, the 235B Quinn model.
So let's bring it home with those results again. The metrics were log score, Breyer score, where lower is better, and ECE for calibration, also lower is better.
And the Foresight trained 32B model, which they call Quinn 332BRL, it just cleaned up. On the Metaculus benchmark, its Breyer score was 0.1793.
Compared to the much larger 235B model's 0.2111, That's a massive improvement.
It's that 27% game. It's a fundamental statement about what matters more, raw scale, or an objective function that's actually aligned with the real-world task.
It suggests that there's a point of diminishing returns with just adding parameters if your training method is naive.
I think so. Better supervision seems to be a far more efficient path to better performance, which, frankly, is great news for anyone who doesn't have a nation-state's budget for training models.
And I want to circle back to the calibration gains. The paper shows the expected calibration error just steadily dropping during training. Why is this method so good at teaching the model to be humble?
It's that log score again. It's just relentless. Anytime the model is overconfident and wrong, it gets a huge penalty. It's a very direct, very painful feedback signal that forces the model to learn to accurately represent its own uncertainty.
It learns not just what it knows, but the boundaries of what it doesn't know.
Which is the holy grail for any system we want to rely on for making real decisions.
So to wrap up the core insight, this work shows you can get incredibly powerful, scalable supervision directly from the world just by letting time pass. You don't need an army of human labelers. Reality provides the label for free.
It does. Now, the authors are very clear about the limitations. This was all done offline, on events that had already resolved. The next step is to make it work online in a continuous feedback loop.
And it's currently just for yes/no questions.
Right. Expanding to continuous outcomes like what will the inflation rate be, or even free text outcomes is the next big challenge. The math should generalize, but the engineering, especially for the resolver, gets a lot harder.
So let's leave our listeners with a final thought to chew on. If this paper proves that delayed objective outcomes are a better training signal for forecasting, what other domains could this unlock?
Well, think about any long horizon task where we currently rely on subjective human feedback because the true outcome is years away. Things like evaluating corporate strategy or even scientific research directions.
Right now, we have experts rate those things.
But what if you could just wait? If you can structure the problem with the same causal discipline, you could potentially train models on tasks where the ground truth only becomes clear after 5 or 10 years. The cost of supervision shifts from human labor to just the passage of time.
You're literally letting the future teach the present. A fascinating and powerful idea.